That's going to be annoying. 12, 11. Yeah, okay, that's fair. So I have to do this in 40-minute sections. Okay, so I'm going to have to, I'll squeeze the second half. Ooh, I have email. Is everybody still there? Are there any questions? No? Everybody is happy? Okay. What did I do in the pen? There it is. Okay. So, let's consider what are the chances of this leaf being really, really deep. And by really deep, I don't mean like depth n, like the worst case. I mean like depth, I don't remember exactly what it was supposed to be. 12 log 4/3 n. Okay? So 12 log 4/3 n, that's why I was saying 120 and you get at most 9. That means, what are the chances that you get a 12th? I think this is how you make the numbers work. So you do so many, you do like 12 times something and you get less than something. So I want log base 4/3 n successes. If I do 12 times that many flips, what are the chances I get fewer than the number I need? Okay, so there is a formula, but so it's called I'm going to skip over this, but it's in Wikipedia. With luck, the scribes will put it in the scribe notes. If I can find scribes for this lecture. It's not that bad. So it's called the Chernoff lower tail bound. And it says that basically it's more general than just coin flips. But if you do a load of coin flips, the probability that you get very, very few heads is small. Okay? So actually, in this case, it's got like an exponent and a delta and a mu. So mu is the mean. Delta is sort of the multiplicative. Okay. I mean, when you plug the numbers in, I believe if you have 12, if you do this many flips, then I did the calculations this morning, and it seems to come out that the chances of not if you do 12 times log base 4/3 n, the chances of not getting at least log base 4/3 n, which is the number of successes you need, is 1 over, well, it's actually, the chances of that are actually smaller than 1 over n to the 4.8. Okay? So if n is pretty big, this is a small number. Okay? So, that means for each branch of the tree, we don't think it's going to go more than 12 times as deep as in the best case. Right? Wow. Okay, the best case is we get an even split. But with this, it's sort of like, okay, we don't think it's going to go more than 12 times. We're going to get, we don't think we're going to have to do more than 12 times as many flips as we want successes. Okay? So, that's the Chernoff lower tail bound, which is very cool and will be on scribe notes. But will probably not be on a test. We gained somebody. Maybe. So, okay. The thing is, why did I choose left the session? Okay, we're back. No, we're still here. Join the session. Okay. Why did I choose 12 to be so big? Like, as I said, if you did 1,200 coin flips and you got fewer than 99 heads, you'd be super convinced that I was cheating. I chose that to be so big because I want this number to be, the denominator to be bigger than n. Why? Because I want to use something called the union bound, which is, if you think about it, suppose, so doing the standard Venn diagram-y thing for probabilities, suppose that this is the whole universe of events, this is the chance of something X happening. This is the chance of something Y happening. This is the chance of X and Y. So this area represents the chance of X happening, this area is the chance of Y happening, the probability, and in here, this, so if I throw a dart at this, the probability is in this circle is X, the probability is in this circle is Y. Obviously the probability proportional to the area that is in here is X and Y. So what's the chance of X or Y? So probability X or Y. Well, notice that X or Y is sort of the probability of X or Y is the probability of X plus the probability of Y minus the probability of X and Y. Right? Looking at this diagram. What's the area of these two circles? It's the area of the X, the area of Y added, and then subtract the area of the intersection. So the key thing is, I don't know about this, right? Maybe in general, if I'm saying what is the probability of some event and what is the probability of some event, if the events are independent, then the probability of this, oh no, sorry. So I don't, I mean there could be, if the events are independent, it's easy enough to work out. But if the events are dependent, then it's a mess. So I don't want to do that, but I just want to say that the probability of X or Y is less than or equal to the probability of X plus the probability of Y. Okay, so that means that when I'm saying, okay, the probability of each leaf being deeper than 12 log base 4 over 3n is less than 1 over n to the 4.8. So what is the probability that that either the first leaf is that deep, or the second leaf is that deep, or the third leaf is that deep? Well, it's at most n. How many leaves are there? N. It's at most n times 1 over n to the 4.8, which is still 1 over n to the 3.8. So the probability that no leaf is that deep is 1 minus 1, is at least 1 minus 1 over n to the 3.8. So the probability, where is my eraser? Yes. So this is called the union bound. So Chernoff bounds are super useful, and you don't have to remember them, you just sort of have to remember how they work, and then you go and look them up when you want them, like I did this morning. And the union bound, this is really easy to remember. Okay, so by the union bound, the probability the tree has height at most 12 log base 4/3 n is at least 1 minus 1 over n to the 3.8. Okay? So this is a bit stronger than the analysis you get in the book, because in the book they talk about the expectation, right? You expect quicksort to work in order n log n time. Here, this is saying the probability that it doesn't work in order n log time is really small. So for example, if n is 1,000, then n to the 3.8 is like a little bit less than 10 to the 12, which is like 1,000, which is a trillion. Okay, so it's a bit less than that, because it's 3.8, because, 10 to the 1 minus, the probability that it takes more than that time is 1 over 1,000 to the 3.8, which is 10 to the 3 times 3.8, which is almost 10 to the 12. Okay. So that's why quicksort is good. Are there any questions? Do people understand that quicksort, if you actually choose your pivot randomly, the probability of it not working well is very small, and it gets smaller as n gets bigger. So that's these kinds of bounds. We say quicksort takes O n log n time with high probability. So, and then people write this as WHP. Okay, it's very common that you say, has anybody seen this phrase, WHP? Hands up. Ding, ding. No? No, nobody's seen this. Is anybody listening to me? No, okay. It turns out that it's some, yes, good, okay, so you believe me. See, some people have seen it. So with high probability bound is better than a bound in expectation, right? Because if somebody says, I don't expect that I don't know, something bad will happen to you. I don't if somebody says, if you go out today, it's not expected that you will get struck by lightning. That means, really, in the weakest sense, that's just meaning like at least half the people who go out today will not get struck by lightning. Whereas we say with high probability, that means like, okay, now I'm relaxed, because it doesn't mean like my chances are. Okay, it's just stronger. Forget my rambling about stuff like that. It means like the expectation tells you something, but with high probability it tells you something much stronger. I will come up with an example and give it to the scribes. Okay, so how much time do I have? I have only half an hour. I'm going to make the scribes put in the argument for quick select, because it's actually very cool. Quick select is like quicksort. You saw it in the tutorial, but it's the one where I want to find like the kth largest element in the set. And so what I do the same thing with the pivot and the split, but then. So if I find out the rank of the pivot, and then I say, okay, well, is the k thing larger or smaller than the pivot? If it's larger, I can throw away all the stuff that's smaller than the pivot and just recurse on that. So it's basically like one branch of the quicksort recursion. The thing is, it's a little bit harder to bound the to get a worst case bound for that. In the book I think they do an expectation as well. The book doesn't have Chernoff bounds in it. I checked in the index. Okay, but for now, I'm going to talk about, until my camera turns itself off again, I'm going to talk about lower bounds on sorting. So the first thing I'm going to tell you is that these has anybody heard somebody say sorting takes, what you've probably heard is somebody say sorting takes order n log n. Either they say sorting takes n log n, or they might say sorting takes order n log n. Ideally, they wouldn't say that, because sorting takes, if you say sorting, remember from the asymptotic notation lecture, if you say sorting takes order n log n, you're saying sorting takes at most about n log n, which doesn't rule out the possibility that sorting takes order n. Right? So, I mean, sorting takes order n log n. It's telling you that you can do it in n log n, but it's not telling you that you can't do it faster. What people want to say is sorting takes big omega n log n in the worst case. Okay, has anybody heard this kind of thing? I want to be able to see people's faces. Okay, somebody. That is not always true. It's true in general, but not always. And I don't just mean that if you're lucky, like the best case of the algorithm, like the best case of, okay, you can always, what? So be careful not worrying, because, for example, the best case of sort of the best case of insertion sort is linear, because you have the unsorted array, you pick an element, and you insert it into your sorted array, which is initially empty. Okay, that takes constant time. Now you pick an element, and you pick the next element, and you go, if the next element, if you're given the array, if you're given, I said I wasn't going to talk about best case, but if you're given n minus 1, or you're given 95, 78, 63, 57, 53, 51, 49, blah, 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 then what are you going to do? You're going to take the 95, you're going to insert it in the list. Now you're going to take the 78, you're going to start here, and you're going to say, okay, where does the 78 go? It goes here. You're going to take the 63, you're going to look at the 78. Every time you start at the beginning of this list, you're going to go here, right? So if you're given a list that's reverse sorted, insertion sort takes linear time. That's not what I mean. That's kind of a pointless thing to observe. What I mean is there are kinds of, there are constraints that can be placed on sorting such that you can sort really quickly. For example, remember when I said 1, 2, 3, 4, 5, 6 up to n? Well, even if I take, even if it's n equals 100, all the elements are distinct, so it's 73, 87, 54, and then 26, and 5. Okay? So the set is a permutation of the elements from 1 to n. How fast can you sort that? Well, if you use comparisons, which is what quicksort does, it takes two elements, it compares them, and on the basis, and it gets, is this bigger than this, or is this bigger than this? Then, if you do it that way, in the worst case, it's going to take n log n, order n log n time, omega n log n time. But, how would you think about it? I mean, I get the feeling some of you have programmed quite a bit before. How would you actually program that? If people have heard this phrase direct addressing, what would you do? You would create an array of sizes. So, I mean, it's sort of, if you know that these are the, if you just have the numbers from 1 to 100, and you know that, then you don't even have to look at the numbers. You just output 1, 2, 3, 4, 5, 6, up to 100. But maybe these have satellite data, right? So this has like some linked list. Each of these have some stuff attached to them, and you want to sort the stuff. Then, so you can't just like output the numbers from 1 to 100. So what you would do is create an array of size 100, and then you go and you look and you put 73. Where does 73 go? 73 goes. It goes in cell 73, right? So if technically, if your array is indexed from 0, you'd have to have an array of size 101, or you'd have to like decrement everything. But that's just like, you can figure that out, I'm sure. So in this case, where you know that you're sorting numbers from a small range, and what I mean is the size of the range that the numbers come from is small in comparison, in polynomial actually, I think polynomial, certainly if it's linear, then you can just create an array of that size. I mean, if it's polynomial, then you have to be a bit tricky. If it's linear, then you just create the array of the size of the range, and you just put it in buckets. Okay, so that takes linear time. So first of all, if you quote me, don't say Travis said sorting always takes n log n time. In general, and especially in the comparison model, and in the worst case, sorting takes n log n time. Omega n log n time. Okay? So, let's prove that. Let's say you have n elements, and you don't know what they are. They're just elements, but they can be compared, so they can be sorted, they can be ordered. Let's suppose that they're all distinct. Right? So you can hold up two elements, and you can look at them. Well, you can't actually look at them, but you can just compare them, right? So suppose, I should have got this right. I thought of getting this right, but I thought, maybe I'm going to have cards of paper, pieces of paper with numbers written on them or something like that. And they're turned over, and you can't see what's written on the fronts. I tell you that there are n distinct numbers written on the fronts, but I don't tell you what those numbers are. And I have 20 minutes, but that's fine, because I can definitely prove this in 20 minutes. Except for Sterling's approximation. No, that's fine, I can still do that too. I can skip that. I can avoid that. Now, so all you can do is you point at two numbers and you say, okay, I want to know which of those two is bigger. And I will tell you that. I will give you that bit of information. Okay? So you sorted, which means that looking at these cards, when you're finished, you know what the original permutation was. Right? If you keep track of, you say, okay, move this card here, move this card here. If you keep track of how the cards move, you can tell me how they were originally arranged. So knowing the sorted order eventually gives you a permutation, and the inverse of that permutation tells you how they were arranged originally. Okay, so let's think about it. You can draw this as a decision tree. So at the beginning, at the root, so let's consider the execution of your algorithm. Now it could be randomized, like quicksort, but just consider a particular execution, which means I can ignore the randomization because I'm interested in the worst case. So you tell me two of these elements to compare, and I give you back the bit that tells you how they compare. Okay, so there's a 0, and there's a 1. Okay. So here you tell me if you want to know is xi less than xj question mark. Okay, and if it is, then you do something, and if it's not, then you do something else. Okay, so now you can say, okay, is xi less than xk? Question mark. And, maybe it is. And so, as you walk down, and then down here, somewhere, you get to a leaf. And this leaf, notice that at some point you get enough information that you can tell me what the original order was. Okay? Now, it cannot be that after you've got so let's say the leaf is where you finally get the last bit and you can tell me that order. It cannot be that this leaf, you could then keep asking questions and get to a different order, because that would mean that you didn't actually have enough information here, because if you keep asking questions you get more information and change your mind. Okay? So every leaf is going to correspond to a permutation. Okay? Now, you can have various actually you can if you want. You can have various ways of getting to the same permutation, but if you think about this tree, you can view your whole sorting procedure as this big decision tree. How many leaves does it have? Well, how many permutations are there? In factorial. How much time does it take in the worst case? It takes however much the depth of the deepest leaf is. That's the height of the tree. Okay? So we can ask, any comparison-based sorting algorithm takes omega h sub n time, well, actually comparisons, where h sub n is the minimum height of a binary tree